Your heart is beating right now at a rate shaped by roughly 3.8 billion years of evolution on a planet with a specific mass, a specific gravitational pull, and a specific relationship between that pull and the fluid, bone, and muscle arranged inside your body. Every system you have is calibrated to that pull. Not approximately calibrated, precisely calibrated in the sense that removing it, even partially, begins producing measurable consequences within hours. Your body does not treat gravity as a feature of the environment it can simply adjust to. It treats gravity the way it treats the rhythm of your own heartbeat. It is written into the operating assumption of every system at once, quietly, continuously, without your awareness, because it is never needed to be questioned. The moment a vehicle accelerates off a launch pad and begins climbing out of Earth's gravitational well, that assumption begins to fail. The forces during ascent are significant, several times the normal gravitational load pressing the crew into their seats, and the cardiovascular system responds by working harder to push blood through vessels being compressed by acceleration. That phase lasts minutes. What comes after it lasts months. Once the vehicle reaches orbit and the engines cut, the gravitational load does not drop to zero in the sense that gravity disappears. It drops to zero in the sense that everything is falling together. The vehicle, the crew, every fluid and organ inside them, all in continuous free fall around the Earth and then away from it toward Mars. The body has no way to distinguish this from the absence of gravity entirely. Every sensor it uses to detect gravitational load goes quiet at once. Within the first hours, fluid that normally pools in the lower body due to the persistent downward pull begins redistributing upward. The legs lose volume, the face and head gain it. The cardiovascular system, receiving signals that suggest fluid levels are too high, responds by shedding fluid through the kidneys. The body genuinely believes it has too much blood. It begins correcting a problem that does not exist, reducing total blood volume by amounts that become significant within days. This is not a malfunction. It is every system working exactly as designed, in an environment the design never accounted for. So what kind of problem do you have when the solution and the problem are the same thing? What does it mean to send a system into an environment where its own correct functioning becomes the source of its degradation? If you like exploring questions like these, feel free to leave a like and subscribe. Tell me where you are watching from, and if there is something about the universe you find yourself wondering about, let me know in the comments. I always wonder which curiosities other people carry around with them. With that said, let's get back to the topic. The fluid shift is only the first consequence, and it is already compounding before the vehicle has left Earth's neighborhood. What comes next is not a separate problem. It is the same problem expressed through a different system, at a scale the fluid shift was only preparing the ground for. The route to Mars is not a straight line. That should be obvious given that both planets are moving, but the implication of it runs deeper than simple geometry. Earth and Mars orbit the Sun at different speeds and different distances, and the relationship between those two orbits means that the window during which a spacecraft can make the journey with a survivable fuel budget opens for only a few weeks every 26 months. Miss the window and the next one is more than 2 years away. Hit it, and the journey still takes between 6 and 9 months depending on the specific trajectory chosen. That duration is not an engineering choice. It is a consequence of orbital mechanics, of the specific way gravity and velocity interact across the distances involved, and no amount of engineering ambition changes the underlying mathematics. The trajectory most likely to be used is called a Hohmann transfer, a path that arcs the spacecraft outward from Earth's orbit until it intersects Mars's orbit at the far end of the arc. It is the most fuel-efficient route available, which matters enormously because fuel mass is one of the hardest constraints in the entire mission. Every kilogram of fuel that has to be carried must itself be lifted out of Earth's gravitational well, which requires more fuel, to lift that fuel, in a compounding relationship that makes the mass budget one of the central physical problems of the mission before a single human being has stepped aboard. The Hohmann transfer solves the fuel problem as well as orbital mechanics allows. What it cannot solve is the time problem. The arc is long, the journey is slow, and the body is degrading the entire time. This is where the two constraints meet in a way that has no clean resolution. A faster trajectory exists. A more direct path that cuts the transit time significantly is physically possible, but it requires vastly more fuel, which requires a much heavier vehicle, which requires even more fuel to lift, compounding in a direction that rapidly exceeds what any currently conceivable launch system can deliver. The engineering response to the time problem is therefore blocked by the mass problem, and the mass problem is a direct consequence of the gravitational physics of leaving Earth. The planet you are departing from is itself one of the primary obstacles to reaching the next one quickly enough to limit the biological damage the journey produces. What this means concretely is that the 6 to 9 month transit is not a temporary inconvenience that better rockets will eventually eliminate. It is a feature of the solar system's architecture that will constrain human Mars missions for the foreseeable future. The body that arrives at Mars will have spent the better part of a year in an environment it was not built for, and it will arrive not at the end of its ordeal, but at the beginning of a new and different one. The transit is the preparation. Mars itself is the exam, and the exam begins the moment the vehicle enters Martian orbit, before a single boot has touched the surface, because the next physical layer is already waiting. Inside the room you are in right now, you are being struck by radiation continuously. Particles arriving from space, high-energy protons and heavier atomic nuclei accelerated to significant fractions of the speed of light by distant supernovae and other violent astrophysical events, are passing through the ceiling, through you, and through the floor without pause. You are not harmed by them in any meaningful way over the course of a normal lifetime, and the reason is above you. Earth's magnetic field, generated by the churning of molten iron in the planet's outer core, extends tens of thousands of kilometers into space and deflects the majority of these particles before they reach the atmosphere. The atmosphere itself absorbs much of what gets through. By the time cosmic radiation reaches a human being standing on the surface, it has been reduced to a level the body can sustain across a normal lifespan without catastrophic consequence. Leave that magnetic field behind, and the situation changes immediately. A spacecraft traveling from Earth to Mars passes through a region of space with no planetary magnetic field offering protection, no thick column of atmosphere overhead, and nothing between the crew and the full unfiltered flux of cosmic radiation that the solar system is continuously bathed in. The particles arriving at the hull of that spacecraft are the same particles that Earth's magnetic field was turning away. They arrive with energies high enough to pass through significant thicknesses of material without slowing meaningfully, and when they pass through a human body at those energies, they do not simply deposit heat the way lower energy radiation does. They interact with the nuclei of the atoms inside cells, breaking molecular bonds, snapping strands of DNA, and producing secondary cascades of lower energy particles that spread the damage outward from the original particle track. The body has repair mechanisms for this kind of damage. They are remarkably effective at low doses, which is why background radiation on Earth's surface is survivable across a full human lifetime. The problem in deep space is not the type of damage, but the rate of it. The dose accumulated during a Mars transit is estimated to be somewhere between the annual exposure limit recommended for radiation workers on Earth and the threshold at which acute radiation syndrome begins to appear, depending on solar activity during the journey. A solar particle event, a sudden burst of radiation from the Sun following a coronal mass ejection, can spike that dose dramatically within hours, producing exposures that compress months of accumulation into a single event. The engineering response to this is shielding, and shielding immediately runs into a physical constraint that makes the problem considerably harder than it appears. The most effective shielding against the low-energy radiation encountered in everyday contexts is dense material, lead being the familiar example. Against the high-energy cosmic rays encountered in deep space, dense materials are not just less effective, they are actively counterproductive beyond a certain thickness, because the incoming particle strikes a nucleus in the shield and produces a spray of secondary particles that can be more biologically damaging in aggregate than the original particle would have been. The physics of high-energy particle interactions means that the intuitive solution makes the problem worse, and the materials that actually help, hydrogen-rich substances like water and polyethylene, are far less effective per kilogram than the dense shielding that cannot be used. The mass budget, already under pressure from the orbital mechanics of the journey, is now being asked to carry the one material that helps least efficiently. The problem with radiation in deep space is not any single event. It is the ledger. Every day of transit, the body is accumulating dose, and dose in the context of ionizing radiation is not like fatigue or muscle soreness, something the body actively recovers from during rest periods and gradually returns to baseline. Radiation damage to DNA is cumulative in a specific and important sense. The repair mechanisms that handle it are working continuously, and they are good at their job, but they are not perfect. A small fraction of the damage they process is either misrepaired, meaning the broken strand is rejoined incorrectly, or unrepaired, meaning it persists in the cell's genetic material. Each misrepair is a mutation. Most mutations are either neutral or trigger the cell to destroy itself before it can replicate. A small fraction survive and replicate, and a small fraction of those become the foundation of a malignancy years or decades later. What changes in deep space is not the mechanism. The mechanism is the same one operating in your body right now, in response to the background radiation you are always receiving. What changes is the rate at which the ledger accumulates entries. On Earth's surface, the rate is low enough that the statistical risk of a radiation-induced malignancy across a full lifetime remains small relative to all the other ways the body can fail. During a Mars transit, the daily dose rate is estimated to be roughly equivalent to receiving a full-body CT scan every 5 to 6 days for the entire journey. That rate does not produce immediate symptoms. It does not announce itself. The crew feels nothing unusual while it is happening. The damage is silent and statistical, accumulating in the background of normal functioning, while every other system in the body is simultaneously dealing with its own set of problems. The cumulative dose across a full Mars mission, transit out, surface stay, and transit back, has been estimated using data from instruments carried aboard robotic spacecraft that have made the journey. The Mars Science Laboratory, the spacecraft that delivered the Curiosity rover, carried a radiation detector during its transit and recorded dose rates that allow reasonable estimates for human exposure. A complete mission under average solar conditions would expose the crew to a dose that current radiation protection guidelines for career astronauts treat as approaching or exceeding acceptable lifetime limits. Those limits are themselves not safety thresholds in an absolute sense. They are risk management thresholds set at levels where the estimated increase in lifetime cancer risk remains within a range that regulatory bodies consider acceptable for professional exposure. A Mars mission pushes against those thresholds before the crew has set foot on the surface. The engineering responses available are genuinely limited by physics. Shielding, as established, has a ceiling imposed by the behavior of high-energy particles in dense materials. Mission duration reduction is constrained by orbital mechanics. The remaining option is pharmacological or biological, either drugs that reduce the cellular damage from radiation or genetic or biological modifications that enhance repair mechanisms. Both are areas of active research. Neither is currently developed to the point where it meaningfully changes the dose calculation for a Mars mission. The ledger keeps accumulating, and what the ledger is counting is not an abstraction. It is the statistical foundation of cancers that may appear a decade or two after the crew returns, in people who will have long since left any mission medical program and returned to ordinary life. While the radiation ledger accumulates silently, a second process is running in parallel that is anything but silent in its physical consequences. Bone is not a static structure. It is a living tissue in continuous negotiation with the forces acting on it, constantly being broken down by one class of cells and rebuilt by another, with the balance between those two processes determined largely by the mechanical load the skeleton is carrying. On Earth, that load is constant and significant. Every time you stand, walk, shift your weight, or simply hold your head upright, your skeleton is registering force and responding by maintaining the density required to handle it. Remove that force and the negotiation tips immediately. The breakdown continues. The rebuilding slows. The skeleton begins losing mass at a rate that has been measured precisely in astronauts aboard the International Space Station, approximately 1 to 2% of bone density per month in the most heavily loaded regions, the lower spine and hips, the same regions most critical for the physical demands of a planetary surface. 6 to 9 months of transit produces a loss that is not trivially recovered. Astronauts returning from long-duration missions on the space station, which is in low Earth orbit and therefore still partially within Earth's gravitational influence, require months of rehabilitation to rebuild bone density and restore the muscular strength that atrophied alongside it. The muscle loss follows a similar logic to the bone loss. Muscle tissue is metabolically expensive, and the body maintains it only to the degree that load demands it. In microgravity, the postural muscles that spend every waking hour on Earth fighting gravity have nothing to fight. They reduce. The cardiovascular system, no longer required to work against gravity to push blood upward from the legs to the brain, reduces its capacity as well. The heart itself loses mass and changes shape in microgravity, becoming more spherical as the constant demand that shaped it disappears. Exercise countermeasures exist and are used on the space station. Crews spend roughly 2 hours each day on resistance and aerobic equipment specifically designed to load the skeleton and cardiovascular system in the absence of gravity. The results are meaningful. Exercise slows the losses significantly compared to doing nothing. It does not stop them. The most advanced exercise equipment currently deployed on the space station, using vacuum cylinders to simulate resistance loads, reduces bone loss to somewhere between half and 2/3 of what would occur without it. The remaining loss continues accumulating across the mission duration regardless. A crew arriving at Mars after 9 months of transit, even one that exercised diligently every single day, will have a skeleton and cardiovascular system measurably compromised relative to departure. This matters for what comes immediately after arrival, in a way that closes one problem directly into the next. The crew does not arrive at Mars and step into a comfortable recovery environment. They arrive at a planet with its own gravitational field, its own surface demands, and its own set of physical requirements that begin the moment the vehicle lands. The body that steps out onto the Martian surface is not the body that left Earth. It is a version of that body that has been systematically weakened by the journey, and it is about to be asked to perform in conditions that would challenge the original. The landing sequence at Mars is itself a physics problem that has no comfortable solution. Mars has an atmosphere, thin enough that it provides almost no useful braking at high altitudes, thick enough that it cannot simply be ignored the way empty space is ignored during orbital maneuvers. A vehicle arriving from deep space is traveling at several kilometers per second relative to the Martian surface, and the atmosphere it encounters as it descends is roughly 1% the density of Earth's at sea level. That 1% does work. It generates heat and some drag. It does not generate nearly enough drag to slow a vehicle of the mass required to carry a human crew to a safe landing speed before the surface arrives. This is the problem NASA engineers have called the 7 minutes of terror in the context of robotic landers, the period during which the vehicle is decelerating through the Martian atmosphere, faster than any signal can travel from Mars to Earth and back, meaning every decision in that sequence has to be made autonomously by the vehicle's own systems. For robotic missions, the mass involved is manageable, and a combination of heat shields, parachutes, and rocket braking has worked reliably enough. For a crewed mission, the mass is an entirely different order of magnitude. A vehicle carrying humans, their life support systems, their food and water, their surface equipment, and the return vehicle is heavy enough that the parachute systems used for robotic landers are physically inadequate. The atmosphere is too thin to slow something that heavy with fabric alone, and the rocket braking required to compensate demands fuel mass that compounds back through the entire mission architecture. The engineering responses under development involve combinations of much larger inflatable heat shields that increase drag surface area, more powerful rocket braking systems, and trajectory designs that extract maximum deceleration from every available meter of atmosphere. Each of these responses is physically achievable in principle. Each adds mass to the vehicle. Each addition of mass requires more fuel. Each requirement for more fuel pushes the launch mass higher, which pushes the cost and complexity of getting the vehicle off Earth higher, which circles back to the orbital mechanics and mass budget problems already established earlier in the chain. The arrival problem does not exist in isolation. It inherits every constraint that preceded it and adds its own on top. Now place the crew inside this sequence. They have spent 6 to 9 months in microgravity. Their bones are less dense, their muscles are reduced, their cardiovascular systems are operating at lower capacity than when they departed. The landing itself subjects them to significant acceleration forces as the vehicle decelerates, forces acting on a body that is already compromised and that has spent months in an environment where no significant forces acted on it at all. The vestibular system, the apparatus in the inner ear that tracks orientation and motion, has been recalibrating itself to microgravity for the entire transit, and now receives a sudden and intense set of signals it has not processed in months. Disorientation, nausea, and impaired coordination are the predictable results, arriving precisely at the moment the crew most needs to be functional, when the vehicle has just landed on another planet, and the immediate post-landing checklist demands clear-headed, physically capable responses. The body that steps onto the Martian surface for the first time does so at its weakest point in the entire mission, and the surface it steps onto is not a neutral environment, waiting patiently for the crew to recover. It is an active physical system with its own demands, beginning with a gravitational field that is neither what the body was built for, nor what the body has been experiencing for the past several months. The gravitational field on Mars is not absent. That would in some ways be simpler. It is present, continuous, and insufficient. At approximately 38% of Earth's gravity, it applies a constant downward force on every structure in the body, but not at the magnitude those structures were built to expect. This creates a condition that is neither microgravity nor normal gravity, but something in between, and that in-between state is not neutral. It is a mismatch. The skeleton that has been losing density for months during transit now begins receiving load again, but the load is reduced. The signaling pathways that regulate bone maintenance respond to force thresholds, not just force presence. On Earth, those thresholds are exceeded continuously through ordinary movement. On Mars, it is not clear that they are exceeded at all. The question is not whether bone loss continues. The question is whether the reduced gravity slows it enough to stabilize, or whether it allows a slower but still persistent decline. The answer is not yet known, because no human body has ever spent long durations under Martian gravity. Muscle follows the same logic. The postural muscles, which on Earth are in constant low-level contraction to counteract gravity, now operate under a reduced demand. They react accordingly. Strength does not return simply because gravity has partially returned. It returns only if the load demands it, and the load on Mars may not be sufficient to fully reverse what was lost during transit. Exercise can compensate, as it does in orbit, but the requirement for constant, structured physical loading becomes a permanent condition of life rather than a temporary countermeasure during travel. The cardiovascular system encounters a similar ambiguity. In microgravity, it adapted to a world in which pumping blood against a gravitational gradient was no longer required. On Mars, that gradient reappears, but at a reduced magnitude. The system must recalibrate again, this time to a value it has never experienced before. The risk is not simply inefficiency, it is instability during the transition, particularly in the early phase after landing, when blood distribution, pressure regulation, and orthostatic tolerance are all being renegotiated simultaneously in a body already operating at reduced capacity. What this creates is not a single failure point, but a chronic condition. The human body on Mars is not in crisis in the way it is in vacuum. It is in a state of continuous partial mismatch with its environment, a mismatch that does not resolve on its own because the environment does not change. The body adapts as far as it can. The remainder of the gap persists, and that gap is only the first layer of what the Martian surface imposes. The atmosphere on Mars is not simply thin. It is thin in a way that places it below the threshold at which human physiology can function at all. Surface pressure averages around 6 millibars, less than 1% of what the human body is calibrated for on Earth. This is not a matter of discomfort or reduced efficiency. It is a boundary condition. Below a certain pressure, the physical behavior of fluids changes, and the body is composed largely of fluids. Water, at this pressure, does not remain liquid at normal body temperature. It transitions toward vapor. The moisture lining the lungs, the thin films that allow oxygen to diffuse into the bloodstream, cannot exist in a stable state. Gas exchange does not degrade gradually. It fails. Oxygen cannot enter the blood in sufficient quantities, and carbon dioxide cannot be removed. The process that sustains cellular metabolism breaks at the interface between the body and its environment. At the same time, the reduction in external pressure alters the equilibrium of gases dissolved in the bloodstream. Nitrogen and other dissolved gases begin to come out of solution, forming bubbles within tissues and blood vessels. This is the same underlying mechanism as decompression sickness, but here it is not triggered by ascent. It is the ambient condition. The body is not transitioning through it. It is exposed to it continuously. What this means is that the distinction between a thin atmosphere and no atmosphere becomes irrelevant from the perspective of human survival. In both cases, the body cannot maintain the internal conditions required for life. The presence of gas above the surface of Mars does not translate into a usable environment. It is not something the body can adapt to. It is something that must be completely replaced. There is no threshold at which a human can gradually acclimate to Martian surface pressure. There is no version of exposure that becomes tolerable over time. Without an artificial environment providing sufficient pressure, survival time is measured in seconds to minutes, not because the body fails slowly, but because the physical conditions required for its operation are absent, which means that stepping onto the Martian surface is not entering a hostile environment in the usual sense. It is stepping into a region where the baseline assumptions of human physiology do not apply at all, and where survival depends entirely on the integrity of the barrier separating the body from that environment. A habitat on Mars is not a building in the conventional sense. It is a pressure vessel. Inside it, the atmosphere must be maintained at a level compatible with human physiology. Outside it, the pressure remains near vacuum. The difference between those two states is not conceptual. It is mechanical. It is a continuous force acting outward on every surface that separates the interior from the exterior. On Earth, structures are not designed to resist internal pressure differentials of this magnitude. The air inside and outside a room exists at nearly the same pressure, so walls carry weight, not expansion forces. On Mars, the situation is reversed. The internal atmosphere pushes outward in all directions, and the structure must contain that force continuously. Every square meter of wall experiences stress. Every seam is a potential failure point. Every joint must hold against a force that does not diminish with time. The magnitude of that force scales with both pressure and size. Increasing the internal pressure to match Earth conditions improves human comfort and reduces physiological risk, but it also increases the outward force the structure must contain. Increasing the size of the habitat increases the total force proportionally. A larger living space is not just more volume, it is a larger mechanical problem. Reducing internal pressure appears at first to ease the constraint. Lower pressure reduces structural stress, allowing for lighter materials and simpler designs. But this introduces a new set of physiological and operational complications. Oxygen concentration must be increased to maintain adequate partial pressure for breathing. Fire risk increases in oxygen-rich environments. Transitions between habitat and spacesuit require careful pressure staging to avoid decompression stress on the body. The system shifts complexity rather than eliminating it. The requirement is not just to establish pressure once, but to maintain it indefinitely. A slow leak is not a minor defect. It is a continuous loss of the medium required for survival. Detecting, locating, and repairing leaks becomes a routine operational necessity. A sudden breach is not damage in the ordinary sense. It is an immediate and critical threat to life, requiring rapid isolation of affected sections and preservation of pressure in the remaining volume. This leads to designs that emphasize redundancy and compartmentalization. Instead of one large open space, habitats are divided into smaller interconnected volumes, each capable of being sealed off. This reduces the impact of a failure, but increases the complexity of the overall system. More walls, more seals, more interfaces, each one another location where integrity must be maintained. What emerges is a system that is not static. It is active, monitored, and continuously managed. The habitat does not simply exist on Mars. It resists Mars at every moment, holding a small region of Earth-like conditions against an external environment that is constantly applying pressure in the opposite direction. And maintaining that resistance, like maintaining temperature, like maintaining life itself, depends on a resource that sits beneath every other solution: energy. Temperature on Mars is not moderated in the way it is on Earth. On Earth, large bodies of liquid water and a dense atmosphere act together as a thermal buffer. Heat is absorbed, stored, and redistributed across the planet, smoothing out extremes between day and night, between regions and between seasons. Mars lacks both of these stabilizing systems. There are no global oceans to store heat, and the atmosphere is too thin to retain or transport it effectively. What remains is a surface exposed directly to solar input during the day and to radiative loss into space at night, with very little in between to slow the transition. The result is a thermal environment defined by rapid and significant swings. A location that is relatively warm under direct sunlight can become intensely cold within hours as the sun sets. For a human habitat, this means that temperature stability cannot be passively maintained. Insulation can slow the rate at which heat is gained or lost, but it cannot eliminate the underlying imbalance. During the day, solar radiation adds energy to the structure. At night, that energy is lost to space through radiation. The system must actively remove heat when there is too much and supply heat when there is too little. This requires thermal control systems that operate continuously, not intermittently. Heat exchangers, radiators, and internal circulation systems become as essential as the structure itself. The habitat is not just holding pressure, it is maintaining a narrow thermal band within an external environment that is constantly pushing it outside that range. The same constraint applies at a smaller scale to spacesuits. A human body generates heat continuously through metabolism. On Earth, that heat is carried away by the surrounding air through convection. On Mars, where the atmosphere is extremely thin, convection is negligible. Heat removal relies primarily on radiation and on active cooling systems built into the suit. Without those systems, the body can overheat even in an environment where the ambient temperature is far below freezing, because the mechanism for removing internally generated heat is limited. At night, the problem reverses. Heat is lost rapidly to the surroundings, and without sufficient insulation and internal heating, both suit and habitat temperatures drop toward the external environment. The system must therefore operate in both directions, adding and removing energy as conditions change. This continuous requirement for thermal regulation feeds directly into the broader constraint that underlies nearly every aspect of surviving on Mars. Pressure must be maintained, temperature must be maintained, life must be maintained. None of these are passive states. Each is an active process, and all of them depend on a consistent and sufficient supply of energy, which means that the question is not simply how to build systems that can function on Mars, but how to power them reliably in an environment that does not easily provide that power. The surface of Mars is covered in material that appears, at first glance, to be familiar. It looks like sand, like fine soil, like something that can be brushed away or sealed out with sufficient care. At a distance, it behaves that way. Up close, and over time, it does not. Martian regolith is composed of extremely fine particles, many of them on the scale of micrometers. These particles are not rounded by water erosion in the way terrestrial dust often is. They are sharp, angular, and abrasive at the microscopic level. When they come into contact with surfaces, they do not simply settle, they interact. electrostatic forces play a significant role. The thin atmosphere and constant exposure to solar radiation allow dust particles to accumulate charge. That charge causes them to adhere to surfaces in a way that is difficult to counteract. They cling to suits, to seals, to mechanical joints, to optical surfaces. Once attached, they are not easily removed. For equipment, this creates a persistent degradation mechanism. Moving parts experience increased wear as abrasive particles work their way into joints and bearings. Seals that are meant to maintain pressure can be compromised as dust accumulates along their interfaces. Radiators and solar panels, critical for thermal control and power generation, lose efficiency as dust layers reduce their ability to exchange heat or absorb sunlight. For human physiology, the risk is more direct. If dust enters a pressurized environment and becomes airborne, it can be inhaled. The same properties that make it abrasive to machinery apply at the level of lung tissue. The particles can irritate and damage the delicate structures involved in gas exchange. In addition, Martian soil is known to contain chemically reactive compounds, including perchlorates, which can interfere with biological processes if introduced into the body. What makes dust a system-level problem is not any single exposure, it is persistence. Dust is not an occasional hazard, it is a constant presence, mobilized by wind, carried across the surface, and repeatedly interacting with every external system, preventing its entry into habitats, removing it from suits, and mitigating its effect on equipment becomes an ongoing operational requirement. This adds another continuous process to the system already in place. Pressure must be maintained, temperature must be controlled, radiation must be managed. Now, contamination must be controlled as well, against a material that is ubiquitous, adhesive, and mechanically and chemically active. And like every other continuous process, the ability to manage it depends on the availability of energy, because the systems that filter air, clean surfaces, and maintain seals do not operate passively. They must be powered, which brings the next constraint into focus, because energy on Mars is not simply a matter of installing a power source. It is limited, variable, and directly affected by the same environment that is already creating the problem. Every system described so far, pressure control, thermal regulation, air processing, water recycling, dust mitigation, has one requirement in common. It does not persist on its own. It must be maintained. And maintenance, at the most fundamental level, is a question of energy. On Earth, energy is ambient. It is available through dense, continuous networks that are largely invisible to the people using them. On Mars, there is no background infrastructure. Every watt must be generated on site, stored, managed, and distributed within a closed system that cannot afford interruption. Solar energy is the most immediately accessible source. Sunlight reaches the Martian surface with less intensity than on Earth due to the greater distance from the Sun, and that reduced input is further complicated by the environment. Dust in the atmosphere scatters incoming light, lowering efficiency even under clear conditions. Dust settling on solar panels reduces output over time. During regional or global dust storms, which can last for weeks, solar generation can drop dramatically, approaching levels that are insufficient to sustain continuous operations. This is not a theoretical limitation. Robotic missions on Mars have experienced significant power loss due to dust accumulation and atmospheric conditions. For a human habitat, the margin for reduced power is much smaller. Systems cannot simply shut down and wait for conditions to improve. Life support, temperature control, and pressure maintenance must continue without interruption. Alternative energy sources exist, most notably nuclear systems. These provide a more stable and continuous power supply, independent of sunlight and less affected by environmental variability. But they introduce their own constraints: mass, heat dissipation, shielding requirements, and the need for reliable long-term operation in an environment where maintenance options are limited and resupply is not available. Energy storage becomes a second layer of the problem. Even with continuous generation, there are periods, night cycles, dust events, system maintenance, where stored energy must bridge the gap. Storage systems add mass, degrade over time, and must be managed carefully to avoid failure modes that could cascade through the entire habitat. What this creates is a dependency chain. Every solution to every other constraint depends on a stable supply of energy, and that supply is itself constrained by the same environment that creates the need for it. If power drops below a certain threshold, systems begin to fail not independently, but together. Pressure regulation weakens, thermal control becomes unstable, air processing slows. Each failure increases stress on the others. In that sense, energy is not just another requirement in the system, it is the condition that allows the system to exist at all. Without it, the barrier between the human body and the Martian environment does not degrade gradually, it collapses. And unlike many other constraints, this one cannot be supplemented from a distance, which leads to the next limitation, one imposed not by engineering, but by the fundamental structure of space itself. The distance between Earth and Mars is not just a matter of scale. It is a constraint defined by the finite speed at which information can travel. Any signal sent between the two planets moves at the speed of light, and even at that maximum possible speed, the delay is unavoidable. Depending on the relative positions of the planets in their orbits, a message takes between roughly 4 and 24 minutes to travel one way. This delay is not a technical limitation. It is not something that can be reduced with better equipment or more powerful transmitters. It is a boundary set by the structure of space-time itself. No system, no matter how advanced, can transmit information faster than that limit. What this means operationally is that real-time communication between Earth and a crew on Mars does not exist. A question cannot be asked and answered in the same moment. A problem cannot be diagnosed interactively. Every exchange is separated by a delay long enough that it fundamentally changes the way decisions are made. On Earth, complex systems are often supported by distributed expertise. When something fails, specialists can be consulted immediately. Data can be shared, analyzed, and responded to in real time. On Mars, that model breaks. By the time a message describing a problem reaches Earth, the situation on Mars has already evolved. By the time a response returns, the original conditions may no longer exist. This forces a shift in where capability resides. Systems must be designed to operate autonomously or with minimal external input. Crews must be trained to diagnose and resolve problems without relying on immediate support. Redundancy is not just about hardware. It extends to knowledge, to procedures, to the ability to improvise within constraints. The delay also affects coordination at a larger scale. Mission planning, updates to procedures, responses to unexpected events. All of these unfold on timescales stretched by communication latency. The crew operates within a local reality that is only intermittently synchronized with Earth. In this sense, distance creates isolation, not just physically, but informationally. Mars is not an extension of Earth's operational environment. It is a separate one, connected by a channel that is reliable but slow, consistent but fundamentally out of step with immediate experience. And that separation becomes even more significant when considering the final phase of the mission, because returning from Mars introduces a constraint that is not about time or communication, but about mass and the energy required to move it. Getting to Mars is only half of the trajectory. Leaving it is a separate problem, governed by the same physics but under tighter constraints. A vehicle on the Martian surface sits at the bottom of another gravitational well, smaller than Earth's, but still absolute. To return, that vehicle must accelerate to escape velocity, enter orbit, and then commit to a trajectory back toward Earth. Every one of those steps requires energy, and in practical terms, that means fuel. The question is not whether fuel is needed, it is how much and where that mass comes from. Launching from Earth already established the central constraint: mass compounds. Every kilogram added to a vehicle requires additional fuel to lift it, and that fuel itself adds mass, which requires more fuel. This relationship does not disappear on Mars. It returns, operating under a lower gravitational pull, but within a system that has far fewer resources available to support it. There are only two viable approaches. The first is to bring the return fuel from Earth. This simplifies operations on Mars, but imposes a severe penalty on the outbound journey. The mass of fuel required for the return must be launched from Earth, carried across interplanetary space, landed safely on Mars, and stored until it is needed. Each step increases the complexity and cost of the mission, and each kilogram added to the outbound mass pushes against the limits already established by orbital mechanics. The second approach is to produce fuel on Mars itself, using local resources. This concept, known as in situ resource utilization, relies on extracting carbon dioxide from the Martian atmosphere and combining it with hydrogen to produce methane and oxygen, a usable rocket propellant. In principle, this reduces the mass that must be launched from Earth. In practice, it introduces a dependency that is just as strict. The equipment required to produce fuel must be delivered to Mars in advance, or alongside the crew. It must function reliably in the Martian environment, processing large quantities of material over extended periods. It must generate not just enough fuel, but enough margin to account for inefficiencies, losses and uncertainties. And it must do all of this using the same constrained energy supply that is already supporting life inside the habitat. This creates a temporal dependency. The return vehicle cannot leave until the fuel is ready. The fuel cannot be produced without functioning systems. The systems cannot function without power, maintenance, and protection from the environment. Each layer depends on the stability of the ones beneath it. Unlike the outbound journey, which can tolerate some degree of uncertainty once it is underway, the return phase is binary. Either the required mass of fuel exists and the vehicle can leave, or it does not and the crew remains on Mars. There is no partial success condition. This makes the return mass problem not just an engineering challenge, but a commitment. A mission to Mars is not complete when the crew arrives. It is only complete when they leave, and leaving requires that a chain of constraints, established months or years earlier, has held without failure. And when viewed across the full duration of the mission, from departure to return, another constraint becomes visible. Not one tied to a single system, but to the accumulation of all of them acting together on the human body over time. Each constraint in the mission does not end when the next one begins. It continues. Radiation exposure accumulates during transit and does not reset on arrival. Bone density lost in microgravity does not fully return before new mechanical demands are introduced. Muscle, cardiovascular capacity, and fluid regulation shift, partially recover, and remain altered while new stressors are layered on top. What results is not a sequence of problems, but a stack. The body is not dealing with radiation, then gravity, then pressure, then temperature. It is dealing with all of them at once, each one operating on its own timeline, each one interacting with the others in ways that are not fully independent. A reduction in cardiovascular capacity affects how the body responds to gravity. Bone loss affects how force is distributed through the skeleton. Radiation damage affects cellular repair across every system simultaneously. Radiation makes this accumulation visible because it is explicitly measurable. The dose received during the outbound journey is added to the dose received on the surface, which is then added to the dose received during the return. There is no mechanism that removes that accumulated exposure. The biological consequences, DNA damage, mutation probability, long-term cancer risk, are integrated across the entire mission duration. Other systems accumulate more subtly. Bone loss during transit may begin to rebuild, but the rate of rebuilding depends on load, nutrition, and time, all of which are constrained. Muscle can be strengthened, but only through continuous effort that competes with other operational demands. Cardiovascular function can recover, but the process introduces periods of instability where the system is neither fully adapted to microgravity nor to planetary gravity. There is no single point at which the body crosses a clearly defined line from safe to unsafe. Instead, there is a gradient. As exposure time increases, as stressors accumulate, the probability of long-term harm rises. Mission planning defines thresholds within that gradient, acceptable risk levels based on current medical understanding, but those thresholds are not physical barriers. They are decisions. The point of no return in this context is not a location in space. It is a region in the mission timeline where the accumulated effects of radiation, deconditioning, and environmental exposure reach levels that cannot be fully mitigated by existing countermeasures. Beyond that region, the mission continues, but the biological cost becomes locked in. What happens afterward is no longer about prevention, it is about living with the outcome. And that outcome is not confined to the duration of the mission. It extends years, sometimes decades into the future, carried forward by the same systems that made the journey possible. When each of these constraints is taken on its own, it appears solvable. We know how to generate power. We know how to build pressure vessels. We understand radiation, orbital mechanics, thermal control, and life support systems in isolation. None of these are mysteries. The difficulty emerges when they are combined. Every solution introduces a cost. Shielding reduces radiation exposure, but increases mass. Increased mass requires more fuel. More fuel increases launch complexity and limits payload elsewhere. Lowering internal pressure reduces structural stress, but increases physiological strain and operational risk. Extending mission duration reduces fuel requirements, but increases cumulative radiation dose and biological degradation. Shortening the mission reduces exposure time, but demands propulsion systems that increase mass beyond current capabilities. There is no single configuration that removes these trade-offs. Each adjustment shifts stress from one part of the system to another. The physics underlying these constraints is not negotiable. The relationship between mass and energy, the behavior of radiation at high energies, the limits imposed by the speed of light, the way pressure differentials act on structures, these are fixed. Engineering does not remove them, it works within them. What remains uncertain is not whether solutions exist in principle, but whether they can coexist within a single system without exceeding the limits of what can be launched, maintained, and survived. The gap is not between knowledge and ignorance. It is between what the laws of physics require and what human biology can tolerate when those requirements are all applied at once. Mars is not unreachable, it is not forbidden, but it exists outside the narrow band of conditions that shape the human body, and reaching it requires constructing an artificial environment that compensates for every deviation from that band continuously without failure across the entire duration of the mission. The result is a system with very little margin, not because we do not understand the problem, but because we understand it well enough to see how tightly constrained it is.